Hi all, this video we're going to introduce the basic functions. So basically functions whose graphs you should know as soon as you look at the equation. That was surprisingly hard to say. So your biggest job is going to be just to memorize what the basic shape of each of these functions looks like. Our goal will be to then apply transformations to them. But for now, we're just going to see the different shapes so that you have a list of what I would expect you to know the graph of. So let's start with the absolute value function. If you've seen these before, great. A lot of times I find that people have seen them before, but if not, we're going through them right now, so don't stress about it. Okay, so the absolute value function looks like a V. Basically what happens is if you plug in an x value 0 or larger, you're going to get back exactly what you started with, which means you're really just on the graph of y equals x over here. But if you plug in a negative x value, you're not going to continue to get y equals x. You're going to get y is the opposite of x. So you'll be on the line y equals negative x. Given one of these graphs, you should be able to find as many points as needed. You have an equation. So it's a matter of picking x and y values and looking for the other one. So if I pick x equals 0, y is also 0. If I pick x equals 5, y is also 5. If I pick x equals negative 2, y is positive 2. If I pick a random x coordinate, the y coordinate will always be the absolute value of that. As we're going through these graphs, I won't go through every detail about every shape, but things for you to kind of think of are you should be able to do this labeling points, of course. You should be able to identify if the graph has any symmetry. You should be able to spot the domain and the range of the function. You should be able to decide if the function, if and when the function is increasing or decreasing, and concave up or concave down. So I'll mention some of those things as graphs show up that I think have interesting characteristics. But again, keep those in mind. That's stuff from the graphs of functions packet, and that all still applies to these graphs. I think only other interesting thing I spot here is this is an even function, so we have that nice symmetry across the y-axis. I think that's it. Okay, so let's look at f of x equals x squared. This is our second basic function. And again, your number one job coming out of this is to make sure that as soon as you see the formula f of x equals absolute value of x, you can picture this graph. As soon as you see the formula f of x equals x squared, you're picturing a parabola with its vertex at the origin. That doesn't quite look symmetric, but this one is also even. So imagine that I'm not crooked. The vertex is at 0, 0. That's going to be a really important point. We'll follow that often when we are doing transformations. It goes through 1, 1. It goes through negative 1/2, 1/4. It goes through negative 3, 9. And again, you have an equation. So in general, if you pick any old x coordinate, the y coordinate is going to be the square of your x coordinate. We get this interesting shape going on here. When you square a number larger than 1, it gets even bigger. So we get fairly steep stuff happening out here on the outsides. When you square a number that's between 0 and 1, it actually shrinks a little, and that gives us this nice rounded out shape at the bottom. When you square negative numbers, you end up with positive numbers. So we only have non-negative y values. We do hit 0, but we don't hit any negative y values. The next one on my list, oh, hold on, getting ahead of myself. Let me see, I mentioned even symmetry. Interesting on this graph, I would say, is the fact that it's always concave up. So we looked at concavity, and this one is definitely always concave up. Even out here where it starts to look like it's straightened out a little bit, it hasn't straightened out completely. It never does. It will maintain this slightly upward bend forever. Okay, f of x equals x cubed. One big difference with this one is when you cube a negative number, you get a negative number. So we won't get the only non-negative y values that we got from x squared. It does have some similarities. If you cube 1, you get 1, so it will also go through the point 1, 1. If you cube 0, you get 0, so it will also go through 0, 0. Other than that, cubing a number makes it bigger, so you will get the, cubing a number bigger than 1 makes it bigger. So you will get the steep sides, and in fact, cubing it will make it bigger than squaring it. So it'll be steeper than x squared out here on the tail. Cubing a number between 0 and 1 will make it small, and in fact, even smaller than x squared. So it's going to be a little flatter at the bottom, and then it's going to get a little steeper than x squared. So if we say this is 0, 0, and this is 1, 1. Again, a little bit flatter than x squared, and then a little bit steeper than x squared as we head off. Mine's not looking very pretty. And then instead of getting a mirror across the y-axis, instead we'll be getting stuff down in quadrant 3. So we will hit -2, -8. And -3, -27, -1, -1, and in general, whatever x coordinate we pick, the y coordinate will be the cube of that x coordinate. Sometimes it bugs people when I label a point that has negative coordinates with just an a cubed, and I just want to remind you, you should not be thinking of variables as representing positive integers. This a could be positive, negative, it could be an integer, it could be a decimal, it could be a fraction, it could be all sorts of things. So don't associate something like that with a variable. This one has odd symmetry. This is the first one we've seen with the odd symmetry, so that's sort of nice. Again, if you rotate 180 degrees, it looks exactly the same. If you flip it over both axes, it looks exactly the same. So this is an odd function. I think a really interesting point on this one is right at the origin. The parabola has a local minimum at the origin. In fact, it is the global minimum. There are no smaller y values anywhere. This one does not get a minimum, but it does get an inflection point. It's definitely concave down, approaching the origin from the left, and it's definitely concave up as we leave the origin to the right. So there is an inflection point right at the origin. Okay, so for the power functions, x squared, x cubed, x to the 4th, x to the 5th, so on, we only count x squared and x cubed as being on our basic functions list for now, but I am going to mention the others just because they come up later in the quarter, and this is a good time to look at them. So x to the 4th actually looks an awful lot like x squared, not identical, but it also will hit 0, 0 and 1, 1 and -1, 1. The difference will be, again, when you raise something to the 4th, if it's bigger than 1, it grows. In fact, it grows more than if you squared it. So this graph will be steeper to the right of 1, 1 and to the left of -1, 1. If you raise something between 0 and 1 to the 4th, it shrinks, and it in fact shrinks even more than the x squared would shrink it. So this is going to be a little flatter at the bottom. So as that power increases, it flattens out the bottom a little more, makes the edges a little bit steeper. So we get another even function, similar but not identical to x squared. X cubed, oh, sorry, not x cubed, x to the 5th looks a lot like x cubed. And we have the same sort of thing happening. It also goes through 1, 1. It also goes through 0, 0. Like x cubed, it goes through -1, -1. But once again, what we'll see is that values between 0 and 1, when we raise them to the 5th power, they shrink quite a bit more than x cubed. So this is even flatter than x cubed. And after the 0.1, 1, this gets even steeper than x cubed. And similarly here, really flat near the origin. And then it gets steep in a really big hurry. I don't know if that's noticeably a lot different than x cubed, but it is a little bit different. You can check those on your calculator if you want to see them together. It's kind of interesting to look at. X to the 6th, as you might be able to guess, looks a lot like x squared and x to the 4th, even flatter in the bottom, even steeper on the outsides. X to the 7th looks a lot like x cubed and x to the 5th, even flatter in the middle, even steeper on the outsides. So those are our power functions. Again, x squared and x cubed are definitely on the list of basic functions. X to the 4th and x to the 5th are to keep in mind for later. Okay, so next on our list for what we're going to use right now is f of x equals the square root of x. So this one looks something like half of a sideways parabola. In fact, that's exactly what it is. It doesn't just look like it. The endpoint is at 0, 0. So here's a really nice visual on the fact that square root functions have domain restrictions. Whatever is under the square root, it has to be greater than or equal to 0. So here we have a domain x greater than or equal to 0. And while we're at it, we can mention that the range is y greater than or equal to 0. So a positive root is not going to output any negative numbers. So you're only going to get non-negative outputs, and you're only allowed to use non-negative inputs. If we want to snag other nice points, nice meaning they have integer coordinates, we better use perfect squares as our inputs. So this does go through 1, 1. It does go through 4, 2. It will also go through 3, 9, and 16, 4, and so on. You don't have to choose perfect squares as your input. So for example, we could say this goes through 3 square root of 3. And in general, a point on this graph will have the form a square root of a. So this is the square root graph. I think interesting things to point out here is this is always concave down and increasing. Always. That never changes. Doesn't show us any nice symmetry. I think that's about all I want to point out for that one. I do have another one that goes with this. These are sort of a pair. I would like to look at the cube root of x. The cube root of x looks kind of like we took a cubic and turned it on its side. In fact, it looks a whole lot like that, and we'll get to the details of that later. So in quadrant 1, it looks similar to, but not exactly like the square root of x. So it does go through 0, 0, and 1, 1. It's a little steeper than the cube root of x, moving away from the origin, and then it's a little flatter after you go through 1, 1. So pretty much the reverse of what we were seeing earlier. Totally acceptable to plug negative numbers into cube roots, so we will get a left-hand side on this one. We don't have the domain restriction. See if I can make this look kind of nice. Okay. And it will go through -1, -1. So this time we aren't going to get points like 4, 2, 9, 3. What we will get is if we plug in a perfect cube, we'll get a nice value. So for example, it goes through 8, 2. The next cube would be 27. Cube root is 3, so 27, 3. You can snag more of these. You don't have to snag nice points. You can snag fractions again. So that looks way too far away. Let's say right here. If we plug in 1/8, the cube root of 1/8 is 1/2, and let's make those negative since I drew my point in quadrant 3. So the cube root of -1/8 is -1/2. And in general, a point on this graph is going to be a cube root of a. So if you want nice points, pick perfect cubes. Again, those are the only two that are on the basic functions list, but I'll just mention, because it's very similar to what happened before, that a fourth root looks a whole lot like a square root. It's a little steeper coming out of the origin, and then a little flatter after we go through 1, 1. Same domain range restrictions. The cube root, so the fifth root is very similar. It's flatter on the outside edges and a little steeper in the middle. So it gets it does get more vertical in the middle, and so on. So the odd roots have this shape, the even roots have this shape. Okay, we're almost done. 2 more. These are our basic rational functions. So the reciprocal function, f of x equals 1 over x, is one of them. And then the other one that I'll look at here is f of x equals 1 over x squared. 1 over x looks like this. It has a vertical asymptote along x equals 0. I know it looks like it's just off to the side, but it's right on the axis. And a horizontal asymptote at y equals 0. What's happening here is that if x is a really, really big number, its reciprocal, 1 over a really big number, is a really tiny number. So the bigger the x value we plug in is, the smaller our y value will get. If x is a really, really tiny number, say 0.1 for starters, we can definitely get smaller, its reciprocal will be a fairly big number. So the reciprocal of 1/10 is 10, the reciprocal of 1/100th is 100, and so on. So the smaller our x coordinate is, the bigger our y coordinate gets. And that's what gives us this asymptotic behavior. We get similar behavior on the left-hand side. It's completely valid to take the reciprocal of negative numbers. You will get back negative numbers. So a really big negative number will have a really small negative number as its reciprocal, and a really tiny negative number will have a really big negative number as its reciprocal. I should point out now, this is kind of looking ahead a little bit too, because we'll come back to these as well as the power functions, that the vertical asymptote is occurring because we actually, well, it's occurring where we actually have this domain problem, right? So x equals 0 is not a valid input, so we will not cross this vertical axis. We're not going to cross over it and come back. The same does not necessarily have to hold for a horizontal asymptote. So here it really does. We don't cross our horizontal asymptote. But there would be nothing wrong with crossing a horizontal asymptote. All the horizontal asymptote is our global behavior. What happens when you have really, really big positive or negative x values. So it wouldn't be a problem to cross a horizontal asymptote a couple of times, as long as you're getting closer and closer to it as you move out the left and right sides of your graph. 1 over x squared is similar. Oh, I didn't label any points. If you want integers, there's not very many choices here. 1, 1 and negative 1, 1, negative 1, negative 1 are both points with 2 integer coordinates. It's not really going to work for anything else, but you can snag points like 3, 1/3 or negative 1/2, negative 2, and in general you can say whatever your x coordinate is, your y coordinate is its reciprocal. So as usual, we can get as many points as we need. So for 1 over x squared, it will also go through the point 1, 1, but it's not going to share any other points in quadrant 1. It will have the same vertical and horizontal asymptotes for the exact same reason. If you plug in a really, really big number and square it and then take its reciprocal, you're getting a tiny number. So we're getting, the bigger our x value is, the closer to 0 our y value is, and it's happening more quickly than before. So this one flattens out a little more quickly. If you square the big number before you take its reciprocal, then what you end up is even tinier than what we ended up with over here. When you take the little numbers and square them and then get the reciprocals, these are actually going to get a little bit bigger faster. So when you square a number between 0 and 1, it actually gets a little smaller. And then when you take the reciprocal, that means it's even bigger than before. And for this one, we won't get any negative y values. So what will happen is when we plug in the negative numbers, they'll get squared, and then we'll take their reciprocal. So we will have stuff happening on the left side of the y-axis, but not below the x-axis. And again, you can snag more points. So this one, what did we say before? 3, 1/3. This one will go through 3, 1/9. So again, just a little bit flatter. We said negative 1/2, negative 2 was on 1 over x. For this one, it would be negative 1/2, positive 4. We square it, we get 1/4. We take its reciprocal, we get 4. So again, a little steeper in the middle. And that's the end of our basic functions list. Let's see if there's anything else I want to point out about these graphs. We've got some nice concavity going up here. This is definitely concave up, concave up. This side on 1 over f of x is concave down, but on 1 over x squared, we have concave up on the left-hand side as well. 1 over x is always decreasing, even though we have that jump in the middle. The function decreases, and then we jump to this side and we get decreasing on this side as well. This one increases to the left of the y-axis and decreases to the right of the y-axis. And we do have some cool symmetry. This one is even. This one I think is even cooler because we don't see it that much. This is symmetric across y equals x. If you fold along that dotted line, the two halves will meet up perfectly, or you can picture flipping it over that line and it should look exactly how it looked to begin with. We haven't really talked about why symmetry across y equals x is an important thing, but we will, so just keep your eyes open for it. Okay, that's it for the list of basic functions. So again, make sure that you dedicate some time to just memorizing what these shapes look like. As soon as you see a square root of x, you should know what the shape of that graph is. As soon as you see a 1 over x squared, you should know what the shape of that graph is. All right, thanks for watching.